The calorie is defined as it takes 1 calorie to heat up 1 gram of water by 1 degree C. So this is why a lot of people remember the specific heat of water. The specific heat of water is 1. And so it's an easy number to remember. Little things like that. And then 1 calorie is equivalent to 4.18 joules. So you can say 4.18 joules. But if you have 10 to the minus 18 joules, that's enough to knock an electron off a hydrogen atom. We call that, when you knock an electron off, what do you call that process?
Emission? Ionization.
Ionization. Emission usually refers to when an electron gets excited and it drops back down, then it emits light. And that's typically emission. But ionization is the physical process of knocking an electron off, creating an ion. Well, this hasn't really been ion. This came from the nucleus of a radioactive atom, and it's missing an electron. There's no electrons in the nucleus. They're just what's found inside the nucleus. Just protons and neutrons.
Since the atom that underwent alpha decay lost it lost protons and neutrons in the form of that helium 2+.
Mm-hmm.
Does that mean that was ionized as well?
No, it already came out as an ion.
Yeah, but now it would have a negative charge, right? Unless the electrons on it also. Like if it was.
Yeah, actually, there were no electrons. You have a nucleus here. There are no electrons in the nucleus, and a chunk of the nucleus breaks off. This chunk we call the alpha particle, and so if this were actually helium, there's another way to make this. The other way to make this is just to take a helium atom, which is neutral, it has 2 protons and 2 neutrons, and then ionize it twice. And so you take an electron off, and you take an electron on. And so you do what we call ionization 1 and ionization 2, and then you can form that. And so since this formed from a different process where there were no electrons there to begin with, and since, rather than calling this a chunk of the radioactive nucleus, since it has 2 protons, we call it helium, because that's the element that all elements are going to be defined by how many protons it has. And so we don't say that this is ionized, but we call this ionizing radiation. Why do we call alpha particles ionizing radiation? Alpha particles are called ionizing radiation. Gamma rays are not particle radiation. Gamma rays are high energy light. And X-rays are called ionizing radiation because what do? They ionize things, basically. And so, alpha particles are extremely unstable because they're missing those 2 electrons. And how big is an alpha particle? Well, when we compare an atom, let's say a hydrogen atom compared to its nucleus, if a hydrogen atom were this big, how big would the nucleus be? It would be hard to see because the nucleus is about 10,000 times smaller than the atom. And so, when you think of a typical 2+ cation, give me a typical 2+ cation. It's a common cation that that's 2+. Calcium. When you think about calcium ions, that's huge. A calcium ion is huge. And a calcium ion is huge and it has a 2+ charge. Well, an alpha particle is tiny. I mean, if this were the calcium ion, we wouldn't even be able to see the nucleus. It'd be so small. And this tiny particle here has a full 2+ charge. Even though these 2 have the same charge, I'll make this a little bigger here, but this would be over-exaggerated in size. That's because in the Rutherford experiment, most of the alpha particles went straight through the gold foil, right? Just a small fraction of them were bounced back or deflected at some moderate angle. But anyway, so in terms of this, and chemists are very interested in electrical interactions. Both of these have the same charge, but they behave totally differently. Which one's more reactive? Would you say a calcium ion or an alpha particle? Alpha particle. And why is that? Why would an alpha particle be more reactive than a calcium ion? They both have the same charge. I'm sorry? Oh, yeah, well, helium's a noble gas. Helium would hate to lose its, the noble gases are unreactive, so they don't want to lose any electrons, actually. But what makes an alpha particle so much more reactive? Yeah, it's related to the noble gas because once it gains those 2 electrons back, it becomes a noble gas.
Because the positive charge of the protons
Really wants those electrons.
Okay, yeah, that's a good point. One point is the positive charge here is more exposed than here, because here a calcium ion has a whole bunch of core electrons. We have core electrons and valence electrons. So there's a core shell or shells around this that will do something called shielding. And so some of the charge could be shielded.
Valence force?
Valence force, meaning for bonding? Yeah, in that sense, yeah, this is going to be much more than this because, oh, now how do you determine what has a higher valence force or not? Periodic table?
Everything going to S basically.
Everything going towards, well, let me put it a different way. What we think of in terms of like concentrated versus dilute, you know, concentrated acid versus dilute acid. Are they the same? Like concentrated HCl versus dilute HCl. Do you treat them the same? No, which one is more reactive? Concentrated HCl or dilute HCl? Concentrated HCl. Even though they're both HCl, if they're both HCl, don't they behave exactly the same? No, I mean, one's more concentrated, one's more dilute. This is the difference. Concentrated charge versus dilute charge here. And so this concentrated charge, the charge is concentrated into a very small volume. And so when we think about chemistry and chemical reactivity, you know, we're always thinking in terms of charge interactions and how concentrated the charge is or how spread out the charge is. And so as far as the 2+ cations go, the common ones would be like beryllium, magnesium, calcium, strontium, barium, and then some others, you know, that are also 2+ in the transition metals. But out of all those, you know, alpha particles are quite a different ion. And they're quite a bit more reactive. Because even beryllium, you know, beryllium, have you heard much about beryllium? Oh, it is found. Beryl. There's a mineral called beryl that contains beryllium that they can extract beryllium from.
Oh,
yeah. Beryllium's a metal. Beryllium's a very lightweight metal, and it's fairly strong like magnesium. You know what they use magnesium for? Like, they use it for things that require light and strong metals, like aluminum. Aluminum's light compared to steel. You know, light being lower density. And so aluminum's density is like, iron's density is closer to like 8, something like that. What is it? I don't have the number off the top of my head. Aluminum's about 2.7 grams per cubic centimeter or grams per milliliter. So aluminum is a lot less dense and it's strong. Like this. I'm leaning against this aluminum rail and it's not breaking or bending. So it's good. It's pretty strong. But there are other strong lightweight metals like magnesium. Calcium's not that strong. Magnesium's pretty strong, so they use that like in automotive applications or aerospace applications. Like they have magnesium wheels. I think on the jet airplanes, they have magnesium wheels because they're so light and they're strong enough to use for wheels. That they put the tires on. When tires get too hot, then that causes trouble because magnesium, like all metals, you know. Can you tell me some properties of metals? They're malleable. It's a physical property.
Most metals are conductive.
Most metals are conductors. In fact, can you think of a metal that's not a conductor? Yeah, copper is one of the best conductors. Lead is a great conductor. You know, I had a dead car battery, and I just bought it. The car battery, I bought it like 3 months ago, and I put it on charger. It wouldn't accept the charge. It kept saying fail, and so I just took it out yesterday. And you know, on the car battery, they have lead posts on there, so I was careful not to touch the post because I don't want to get lead poisoning. Aluminum? Aluminum is a great conductor of electricity too. Yeah. Watch out. Aluminum is a good conductor of electricity. So beryllium was used a lot in the South Bay here in aerospace. There are a bunch of people who machined beryllium for aerospace application. But it turned out those people who were machining the beryllium all ended up dying of the same thing. Some form, I think it was. It's been a while since I looked it up. But some beryllium poisoning, which caused this disease or cancer or something, and then they stopped, using it. And beryllium, why is beryllium so toxic? It wasn't like something that was acute, like they got exposed to beryllium and then they died suddenly. It was long term. In your body? Yeah, exactly. Yeah. So we need magnesium and calcium in our body, but beryllium is a lot more reactive because it is bigger or smaller. It's smaller. And so what happens is beryllium replaces magnesium and calcium in the body and gets stuck there and prevents things from properly functioning. And so we're always thinking about these kinds of things, charge and size. And sometimes we call that charge density. And so alpha particles are extremely dangerous because of their high charge to size ratio, extremely small size. And so compared to beryllium, beryllium are relatively safe compared to alpha particles. Alpha particles are going to be extremely reactive because they bond electrons. And they're going to take those electrons. When they take those electrons, they form ions in the weight of taking those electrons. But anyway, so this person was looking at bombarding yeast with gamma radiation and seeing what happened to the metabolism. But that was electromagnetic radiation. We have two types of radiation. This is particle radiation here, the alpha particles. However, with the gamma radiation, when you use gamma radiation, you need lead. Why lead?
It blocks it.
It blocks it. What makes lead so good at blocking radiation? Yeah, that's one, but it's not just the density, because electromagnetic radiation consists of electric and magnetic fields, these oscillating fields traveling at the speed of light. What makes it so good at absorbing radiation is it has a lot of electrons. And those electrons interact with these electric fields. Electrons are negative. Electric fields are oscillating positive and negative. And so these electrons can absorb a lot of these high energy. And since lead has a lot of electrons, that's what's used, lead. Unfortunately, lead is a little bit toxic, so if you do use lead, like when I got some x-rays recently, they gave me a lead apron, to protect from ionizing radiation, to absorb it. If you use gamma rays, you don't use lead apron, you have to use lead bricks. And so they have these heavy bricks that you put around there to protect yourself from that radiation. There are things with more electrons than lead, but why not use those? Because lead is a bit toxic. Well, what else could you use? Could you use polonium, PO? Lead has how many electrons? 82 electrons. How about bismuth? Well, bismuth isn't so malleable, it isn't so ductile, because bismuth is getting in from more metallic to less metallic. It's going through that range. You know, that transition range, what do we call that? The alloys? Okay, we have the metals on the left, and we have the non-metals on the right, and then that zone, the metalloids. Yeah, that's it. Did you say metalloids? All right, I'm sorry. I thought you said alloys. All right, you're right. And so it's not, you know. And then what happens? Take a look at what happens. What's going on with polonium? PO. Polonium. Why? What is that number? Do you see the 209 there? Why is that in parentheses?
Is it not consistent?
Well, it's maybe they don't have the precision there or something. Maybe, I don't know. Non-consistent? Yeah, consistency is related to precision. Yeah, and so it's something that's very precise is very consistent, very well known to a high degree of precision.
Is it rare?
It's a bit rare, yeah. It's a bit rare. Although the polonium was in the news recently, I read a story about polonium in LAX. Did you read that?
No, I didn't. But I do have a question.
Uh-huh.
How do you spell polonium? Is it POLONIUM?
Mm-hmm.
Isn't that made from radioactive material?
It's not made. It is, yes, but it is itself radioactive. You haven't heard of polonium before. Polonium. Have you heard of the polonium T? In the UK and also in Los Angeles here. Did you hear about that? There's some kind of. This is all like this. Well, anyway, apparently there were 2 people in LA that were poisoned with polonium, and there are people in Europe that were poisoned with polonium in their tea or something like that to try to kill them. This is an extremely excruciating method of death, because if you drink the polonium, okay, now you have polonium, and polonium is an alpha emitter. And it's emitting these alpha particles. Causing damage, ionizing, it's ionizing radiation. And so, there are certain things that you can do. Polonium is also a heavy metal, so, you might try to get rid of the polonium. How can you get rid of the polonium? What can you do for heavy metal poisoning? Is there a way you can do that? There are, people use these things called chelating agents. Have you heard of those? Things like EDTA. Have you heard of EDTA? Ethylene diamine tetraacetate chelation therapy. But, I'm sure they did that. They did the chelation, they did that, but they couldn't get rid of all of it. I think they might have survived with crippling disease. I'll have to look at it again, but really, it's pretty... you wouldn't think in Los Angeles, and then the polonium, if let's say you're the busboy at the restaurant where they found polonium traces everywhere. It makes you wonder, if you're cleaning up the glass, contaminated with polonium, and ingest it. Yeah. Well, lead. Why lead? Lead is like kind of the last stable element. Once you go past lead, do you see polonium? And then you see radon there? Radon 86, alpha emitter. Actually, at my house, I have a radon detector. Because some of the soils, especially granitic soils, release radon into the air. You inhale radon, starts to cause damage, to your lung. It's an alpha emitter. So it's really easy to protect yourself from alpha particles, though. Because alpha particles are so ionizing, a sheet of paper. If you have a sheet of paper, the alpha particles will immediately strip the electrons off the paper and form helium. And helium's non-toxic, basically, unless you die of asphyxiation. But it's easy to protect yourself. But if you inhale this or you ingest it, then it's hard to protect yourself from this. Well, I went off on a bit of a tangent, but it's just to see. We're going to be reviewing some of the concepts. It's easy to forget, right? It's easy to forget a lot of things, or you might not have heard it, you know. But a lot of this is kind of familiar, right? All right, let's take a look. This is the Canvas page. So I put in week 1 here, the syllabus and the course info. Let's take a look at the course. My office is down the hall. It's in room Chem 120. This email, and you can reach me at this number here, extension 3240. I haven't figured out my office hours yet, but I'm thinking it's likely it's going to be Tuesday before this class and after the afternoon class. Afternoon class ends around 2:30, I think, and then maybe a remote or online office on Monday. We'll figure it out. Yeah. Here's the catalog course description. Now we're going to be studying matter, elements, compounds, mixtures, chemical reactions, etc. This is a dictionary definition. I like this one, number 2 here. The composition, structure, properties, and reactions of a substance. In chemistry, we have 2 types of properties. What are the 2 types of properties that we have? Or at least we break it down into 2 types of properties. Physical and chemical. And so they must be talking the composition, structure, physical properties, and reactions, i.e. chemical properties of a substance. Or we can just get rid of this reaction. So chemists would define this a little differently. Chemists would say just the composition, structure, and properties of a substance. No, we don't just study substances. What's the difference between a substance and what? I mean, how would a chemist define a substance?
Pure.
Pure. Like, and if it's pure, then it's got to be either a what or what? If it's pure, it's got to be a what or a what? 2 things, blank and or a blank. Element or compound, yeah. So if it's pure, it's got to be an element or compound. Elements have fixed composition. It's just the element. And compounds have fixed composition, right? Versus what that doesn't have fixed composition? What doesn't have fixed composition? Mixtures. But, we study substances and we study mixtures, like hydrochloric acid. And therefore, I wouldn't narrow it down to substance. I'd say just the composition, structure, properties of, and to have something totally broad, we just say matter. Matter is what?
The physical material.
The physical material of the universe, so whatever it is, we'll study it. And so that's, and the physical material could consist of mixtures, etc., substances. The course objective here. We want this, upon successful completion of this course, you should have a background comparable to CSU or UC campus. So the book we use is this one. It's expensive. Actually, the if you buy this new, it's pretty expensive. But this book is getting old now, so you can find it pretty cheap. Used book online. I was looking at it, and I saw one for like $5 or something. It was. I'm not sure what condition it's in, but there, and I'm sure there are other, other places you can get this as well. But at the bookstore, this is how much? Did anybody buy this? Bookstores.
I was over there about a couple of minutes ago, but I did not buy it.
You didn't buy it? How much was it?
I actually did not ask.
Just
We couldn't find it.
Oh, it's on the tag underneath. I think it's like $160 or something, $200. But it's a good book.
Will it be required in the class, or if I have it as an ebook at home on my computer?
Yeah, you don't need to bring this to class. You could have it as an ebook. I have it as an ebook. So I probably won't bring this much to class. But yeah, the bookstore has it, and it's good to invest in a book because this could serve as reference. When you forget things, you can go back and review it. Okay, this is also highly recommended here, although the bookstore doesn't sell this, I think. But you can find it online. It's the complete, it's almost complete. We should say almost complete solutions manual, because there are some problems that aren't in here. Not that many, but some. And although there are some errors in here, because the authors of this, there are a lot of people working on this. But anyway, it's worth getting the complete solutions manual. When I was a student at UCLA, I always tried to get the complete solutions manual. And at UCLA, they had it. For all the classes I took that had a complete solutions manual, they gave it. Why? They gave it because the exams were, you probably heard this, the exams were, a lot of people say the exams were harder than the homework or nothing like the homework. Have you heard that? Yeah. Well, that's why they give the complete solutions manual, because the exams aren't exactly like the homework, but kind of the same. So look for that. I know there are some electronic copies floating around, but it's worth getting. I assume you all have the prerequisite for the course. We'll skip that. So the required materials. So if you have an earlier edition, that works too, like the 10th edition. Actually, when I was a student, you know what general chemistry book I used? I used Petrucci, but it was like the 8th edition or something like that. Or maybe even earlier, 1st edition. But anyway, so you can find, the 8th, 9th, probably the 10th edition is very similar. The 9th edition is quite similar too. But you can find the 11th pretty cheap. It's 2017. The level of the book, though, this is why it's not as popular. This book is between, let's say, a majors, like if you're a chem major, and an honors level book. And so this is kind of like the honors level textbook for chem. And so that means it's a little bit more rigorous than your typical textbook, which is good because at UCLA, they use high level textbooks for Gen Chem. Then there's the lab manual and supplement. This is like a shrink wrap and plastic wrap. It's not binded. It's just 3-hole punch. You can put this into a binder, and that's going to be our lab manual. So you'll need that. 3, you'll need a scientific calculator. if you're looking for, if you already have a calculator, that's good. I'm sure you do, but if you're looking for a calculator, I like this one a lot. This is the Casio FX115 ES. I like this calculator a lot because this calculator solves quadratic. It actually solves up to cubic equations, like third order. And that's always a nice thing to have, especially for Chem 1B. In Chem 1B, you have to solve a lot of quadratic formulas, and it gets tiresome to do them by hand, with the quadratic formula. So it's nice to have a calculator that does that. Okay, you'll need a comp notebook. If they don't have any quad ruled, which is the graph paper, then you can just get college ruled. This is the comp notebook, which is just your standard, which I forgot to bring, but let's see if I have one. Yeah, these are some from past students. So yeah, this is what we're going to take our lab observations, our notes on. So this is from Chem 1A. Usually with the comp notebook, we'll save the first page. This is very nice, table of contents. List it, and then number all the pages. Write the notes here. This person just did college ruled. That's okay. Accept that as well. If you can't find a quad ruled. Let's see this one. They sell these in the bookstore too. They have a little larger format one in the arts and engineering section. I think there's a couple of dollars. You'll need goggles. The goggles that we have are visor goggles. I think we still have a bunch of used pairs after the pandemic shut down. A lot of people didn't come back to get their goggles. We have a lot of goggles, so if you don't have some and you want a free pair of used ones, you can just grab them. Optional. This is optional here, but this is required at other schools. So you probably want to start getting used to it. So for example, lab coat is required at UCLA. Nitrile gloves are required at UCLA. But here they're optional, so it's up to you. But the lab coat is nice to have, and you can get them for pretty cheap now. The last lab coat I bought was about $15 on Amazon. The bookstore is carrying lab coats now too. And mine was cheap because mine wasn't 100% cotton. When I was a student at UCLA, we had to buy 100% cotton lab coats. And that's because of fire. You didn't want any kind of synthetic materials that were combustible. And so the lab coat I bought at UCLA, that was about $70, but that was now in today's dollars, it'd probably be like $150 in today's dollars. Actually. But the $15 lab coat's fine. It's just to protect your clothing from splashes. In lab, I never wear nice clothing in lab because usually I get splashes up, and then after you wash it, then you'll see the holes that appear from the splashes. Nitrile gloves are better. Nitrile are more breathable. They're easier to work with, I think, than latex. And so I'd recommend those. And nitrile has better protection from most of the solutions that we're using. And so nitrile you can get pretty much anywhere. There are going to be no dropped exams or dropped labs, pretty much. All this stuff is required. Attendance in lab is mandatory. You have to come to lab. And so, if you have excessive absences in lab, then you might be dropped from the course. And so, lab is very important here. But the lab accounts for just maybe, let's see, 20% of your grade, roughly, a little more than 20% of your grade. So some people think 20%. I can skip all the labs and still pass the course. But unfortunately, you can't. Because like at UCLA, they separate it. You have a lab course, which is an entirely separate course than the lecture course. So you could fail the lab course and you fail the lab, but that's not going to impact your lecture. Here, we combine the lecture and the lab. In order to do that, UCLA and the UCs and CSUs require us to have this contingency here, where if you fail lab, you're going to fail the class. So you could be getting an A in the lecture and an F in the lab. Unfortunately, you're going to get an F for the whole course. So that's another reason labs are critical to attend. But you know, things can happen. So if things happen, make sure you contact me. Sometimes you can make up the lab. You know, we have an afternoon section here too. So if there's space, you know, you can work both morning and afternoon to try to catch up. Some of the labs we can't make up because of the equipment. So we just take it case by case. All right, then we have exams. We're going to have 3 midterm exams. These are 100 points each. It's going to be 300 points. And then the final exam is going to be about 20% of your grade. It's going to be 200 points here. The lab's going to consist of standard reports, and then we're going to do 2 formal lab reports. The formal lab reports is going to follow a certain format that's common in science. And then we have a lab technique grade, which is about 10 points. This is the breakdown here. And so the cutoff for an A is 88%. And a B will be 78%. A C is going to be 65%. Okay, those are pretty fixed based on past data. So it's a little bit curved to begin with. If you have any special needs or requirements, let me know. Or there's a special resources center on campus. You can make arrangements with them. I forgot to delete this. I'm not using Piazza anymore because they started charging a fee. So I'll just announce anything will be announced in Canvas. All right, a note on cheating. Academic honesty is mandatory. You know, different professors have different philosophies regarding this. You know, in lower division, some professors, they don't do anything. Because what they do is they figure, you know, once you get to upper division, there's no way you can hide, you know, if you're cheating. It's going to be so obvious, you know, that you really don't belong in the class, basically, if you cheated your way through the lower division stuff. And so that's their philosophy. I have some kind of intermediate philosophy there. But, you know, if we're doing this, just try to stay on top of the material. And staying on top of the material, we have free tutoring in the library. The tutor in the library is actually a former student of mine. He had Chem 1A, so I think he's pretty familiar with it. The MESA program, I'm sure they're going to have facilitator-led groups. And, you know, our book has its website. There's some practice tests, practice quizzes you can take on there. Khan Academy, etc. I'm sure there are a bunch of others. I haven't been keeping up with this. Other textbooks, too. You know, some things might not make sense in Petrucci. And so just grab another. We have some books. You know the Chem study room over there? We have some other textbooks in there. Just grab another book and read, you know, that author's take on the material. It's something I did a lot. And then just have this little footnote here about studying. You read that. See what you think. Oftentimes, you just kind of have to find what works for you. What works for other people might not work so well. I tried lots of different things. So this is kind of what I came up with. This. Okay. Let's take a look at this a little bit. So today we're covering chapter 1. We're going to start chapter 2 and get into chapter 3 this week. Monday's a holiday. And so we go through the topics. Monday and Wednesdays are lab days there. And so let's see what is our first lab. Our first lab is here. It's called Experiment A. It's measurement. It'll be on Thursday next week. This one you won't need safety goggles. Experiment 14, we're going to do titration right off. So, two-part titration, 14A and 14B. Here you'll need safety goggles and closed-toe shoes. No sandals. Although, the weather's not really sandal weather. Okay, 17, we'll need goggles. So, probably you won't need goggles until the third week. When's our first exam? Yeah. Our first exam is going to be here. So this is the first week, second week, third week, fourth week. And in the middle of the fourth week, Wednesday, our exam. It'll be a lab day. And so we'll just use the whole period for the exam. The exam's going to cover chapters 1 through 4, the first test. And then about 4 weeks after that, we'll have another exam. Exam 2, we'll cover chapters 5, 6, and part of 7. 7 is a very long chapter. Probably depends, these are just targets. As we get closer, we'll see. Then we'll have spring break. And then after spring break, we'll have exam 3. 7, 8, 9, 10. And then we have about 4 weeks to the final. 16-week semester. So I'm not going to have an exam 4. So this latter material really covered. Actually, we're going to have a 2-part final here. Final part 1 to be 3 hours, and final part 2 is like a regular lecture day, which is an hour and a half. So this will be mostly multiple choice, I think, and this will be some free response questions here. And so break it up into 2 parts. I don't. I have the old tests you could use as a study guide, but I don't make study guides for the test. The reason I don't make study guides is because of the way I recommend people study. The way I recommend that people study is they make their own study guide. They make their own study guide by taking notes and then using those notes as your study guide. And so the way I did my classes when I was a student is I just took as detailed notes as possible and tried to make it sure that there was as complete as possible. And then I reviewed those every day. And so, by the time the exam came, I had it all memorized, all this stuff memorized. And then you think, memorization, that's weak, that's not really learning. But actually it is learning, because if you have all that stuff memorized, it's like, the way I like to think of it is like this, let's say you're in a new city and you're following directions, navigation directions. So turn right here, turn left there. And you're paying attention to these directions. Okay, I was listening to one Chem 4 instructor. They say, okay, step 1, grams to moles. Step 2, moles to grams, or moles to moles and moles to grams, or something like that. And so I was thinking, oh, this is like the directions, these directions. But eventually, you memorize the directions, and eventually, once you memorize the directions, you know where you're going. And once you know where you're going, then you can look around and see what else is there. But initially, when you're going there, you have the blinds on and you don't see other stuff. So the analogy is that once you memorize that, you have that stuff down. So if you have the stuff down here, then you can start looking at deeper things, higher level things, more complex problems, that kind of stuff. And so that's kind of what they expect. They expect you to have all the basic stuff down, like memorized, and that way you can work on the more complicated stuff. And so the types of tests that I found at UCLA were, okay, like 90% basic, 10% beyond, beyond the stuff in the homework, beyond the stuff in the textbook. That's what I found. And the stuff that's beyond you can get, if you have the basics down pat. And so you could use those on the old exams. In fact, I didn't realize this, but that's like this stuff I learned after, but well, nowadays you got the internet, so there are test banks, but there's like Division I, superstar swimmer in my class, only came for the exams. That's it. I thought, only came for the exams. How did he pass the class? But that guy had tutors, and then they have, I didn't know, they had the test bank there, and they had the access to all these old tests that they could use to study. And I thought, wow, that's kind of unfair advantage, I thought at the time. And then the same thing with like the fraternities and the sororities, they keep test banks there. But now they have test banks everywhere. And so that's an advantage. So then I just thought, oh, I'll just make the test available. If I have an old test, I'll just give it to everybody. Keep it fair that way. That's what I was thinking. It's not that I'm going to make the exam exactly the same. But anyway, so let's see. So there will be a little bit more of the latter chapters in here. And then these are comprehensive, so they'll cover all the chapters with a little bit of bias towards the end chapters. Okay, any questions on this? So those are the tasks. We're also going to have quizzes. These quizzes are just going to be spread out during the semester. And they'll be small quizzes, not worth that many. In fact, we're going to have a quiz coming up. Maybe we'll have a quiz tomorrow. But I was thinking we're going to have a quiz tomorrow because I want people to start. Well, a lot of people already know these, but I want people to start memorizing stuff right off the bat. And what are the most common, let's say, what are the most common acids? What do you think are the most common acids? Hydrochloric. What's the formula for hydrochloric acid? HCl. So what I'm going to do is I'm going to give you a quiz. I'm going to say hydrochloric acid, and you're going to write the formula. Here, HCl. Okay, give me some other common acids. Give me 5 of the most common acids you can think of.
Hydrochloric.
Which one?
Hydrochloric.
Hydrochloric. Fortunately, hydrofluoric, is that a strong acid or weak acid? It's a weak acid, but it's a very dangerous acid. If you have give me another weak acid. Well, NH3 we usually, that's on the opposite end, the base end. It's a weak base, though.
Nitrous acid?
Nitrous acid is a weak acid, but what's a more common? People eat this stuff. People eat it. And in fact, I was at the store, and this person was saying, I want salt and chips. I'm looking for salt and vinegar chips. And apparently, people love this stuff. It's sour. But what is vinegar made of?
Expired wine.
So I have a story. Maybe it's a funny story, but I have a story about wine that hit me. Acetic acid, right? So hydrofluoric versus acetic, both are weak acids. Would you treat both the same? No, not at all. I mean, vinegar, okay, I'll eat it. You know, I like dressing, but Italian dressing. But what about hydrofluoric? If you ran out of vinegar, would you grab a bottle of hydrofluoric? It's weak acid, sour. You know, add some flavor to your dressing. Would you? No. No. Actually, you should. They took a lot of these down, but there's a whole bunch of gruesome pictures of hydrofluoric acid burns. Gruesome. They use hydrofluoric acid to etch glass. When I was at UCSB, I walked into the engineering department. In the engineering department, they have they call it the wall of horrors. This is electrical engineering, and they just show pictures of the accidents that happened there. You know, the wall of horrors. And one of those is hydrofluoric acid burns. They use hydrofluoric to etch semiconductors. And hydrofluoric acid burns, you know what you do for hydrofluoric? It doesn't really burn until it hits your bone. When it hits your bone, then it's excruciatingly painful because it's not because of the acid. The acid just mildly burns your flesh like acetic, but it's because it undergoes a precipitation reaction, and it precipitates out calcium fluoride. This is called metathesis. It's not because of the acid properties, it's because of the metathesis properties of hydrofluoric acid, which makes it so dangerous. And so one of the antidotes is calcium injection. So they have some calcium, I forgot the anion, some organic anion that they use, and you inject yourself with it. So hopefully that calcium injection will eat up the fluoride, which is going to cause you excruciating pain. But not hydrofluoric. Acetic is a good one. Let's go with acetic. What's the formula for acetic acid? HC2 H3O2. Okay, that's good. Good memory. Okay, what else? Sulfuric acid. Okay, what's the formula for sulfuric acid? H2SO4. 3. We'll think of two more. Carbonic acid. Carbonic acid is very common. It's unstable, though. Decomposes into CO2 and water. So carbonic acid, we can't buy a bottle off this shelf of carbonic acid. We just buy like carbonated water. That would be our carbonic acid. Nitric acid. That's a big one, too. Nitric. What's the formula for nitric? HNO3. And phosphoric acid is really common. We should do that too. What's the formula for phosphoric acid? H3PO4. Good. And this one, which we're going to use in our titration experiment, an acid that begins with O, the letter O. Oxalic acid. Formula for oxalic acid? H2C2O4. Good. You're going to do well on the quiz. Let's have a quiz. Let's have a quiz tomorrow. We're going to have a quiz. It's going to involve these acids here. So I'm going to quiz you. And it's going to be, you've got to get it right. Because there's going to be no partial credit on this quiz. It's either going to be right or wrong, the formula. Can you do that?
Is it just acids?
Just acids. Just these acids here.
Just those?
Yeah, just these acids here. You know, the one thing that's you know, when you have the common acid and you're in Chem 1A and you get the formula wrong for one of these common acids, then it's not. You want to be at a certain level where these are easy. All right, so this is going to be the quiz. This is the formula tomorrow for these acids. And so that's going to be kind of like the quizzes. We'll have different kinds of quizzes, so we'll see as we go along. Let's take a break.